Hi students, let's continue with the dual nature of matter and radiations. So topic last class we have discussed and we'll continue the same thing. And today we are going to do a few set of questions what we have learned based upon the concept of stopping potential, threshold frequency, threshold wavelength, whatever we have seen in the last theory sessions. We are going to do a couple of problems, then we'll enter into the next topic. Okay. So before that, I want you have to recollect the things in which you have already learned. Okay, in case if you are remembering, it is well and fine. In case if you are not remembering, pause the video and take the next 15 to 20 minutes of time to go back and revise it, the major formula, the major concept, just to go through at least once before entering to the question, so that you will understand. It's a kind of quick revisions. So I will write the questions will be here and then we will see. Okay. The first question is, the following plot represent, the following plot means graph, the following plot represent the variation of stopping potential, the variation of stopping potential with respect to 1 by lambda. Which of the following statement is correct? Which of the following statement is correct? Okay, which of the following statement is correct? Okay, first we will have a plot for this one, then we will see 1, 2 and 3. This is with respect to 1 by lambda with V, and this is metal 1, this is given as metal 1, and this is given as metal 2, and this is given as metal 3. This is like 0.001, 0.002, 0.003. Okay. So, 3 things are given, 3 materials have given, not materials, 3 metals have given, and whose 1 by, this is 0.004, okay, 1 by lambda values are given. Which of the following statement is true? That's a question. So, we will have a couple of options. Phi 1 is to, phi 2 is to, phi 3 is equal to 1 is to 2 is to 4. Phi 1 is to, phi 2 is to, phi 3 is equal to 4 is to 2 is to 1. Okay, what is this phi 1, phi 2, phi 3? Phi 1, phi 2 are the work function. So the ratio of the 3 metals work functions are given as phi 1, phi 2, phi 3. And the third one, tan theta is proportional to, tan theta is proportional to HC by E. Tan theta, what is called tan theta? Tan theta is the slope of the graph. Okay, tan theta is the slope of the graph. Next one, the violet color can eject electrons from metal 2 and metal 3. So what this indicates? A violet color which can eject electrons from metal 2 and 3. So 4 options are given and graph is given. Looks like initially it is complex, but it is a very simple concepts are involved in this question. So you want to know the theory in which we have learned in the previous sessions, then only this question will be easy. So this is a plot, this is a graph which is given will be there, and we need to find out which of the following statement is true. Before going to this topic, I would like to give one additional information. See, if you are giving the plot between, we have already drawn the graph between the stopping potential, there V naught is called the stopping potential. Here here in the question it is given as V. So here V means stopping potential, that's all. In theory we have learned about V naught. So in the theory whatever we have learned, V naught and the V both are same here, there is no difference in short. So V with the 1 by lambda graph already we have drawn Hope it is already there in the notebook also. If you go and look, V0 versus 1 by lambda graph is there. Okay, now if the same graph is asking, so I remember the graph we have learned 1 by lambda is like this. We have a graph like this. This is already we learned. Suppose if the question is asking with respect to V0 versus 1 by V0 versus lambda. V0 versus lambda. V0 versus it's not 1 by lambda, V0 versus lambda. Then the graph will be in a reverse way. It's a slanting like this position. Just understand this is an additional information so I am giving to you before entering to the question. Now we have a graph which is given will be there. I'll keep the options will be there. Metal 1, metal 2, metal 3. This area I am clearing. I am going to answer in this left side. Okay. So fine. Perfect. Okay, so we have to find out the work function and we'll see which of the following is matches with the options is given to us. What is the value of work functions? Work function general formula HC by lambda 0. HC by lambda 0, or we also written as HF naught. C by lambda 0 is called F naught. So lambda 1 by lambda value is given in the question. So phi 1 is to phi 2 is to phi 3 is equal to HC by 1 by lambda value is given. How much for first metal? 0.01. That is to HC into 0.02, 0.01. And that value is to third metal HC by lambda 03. Okay, for the third metal. So I will write an intermediate step also. So that's very clear. HC by lambda 01 is equal to HC by lambda 02 is to HC by lambda 03. What is 1 by lambda 0? It is given the values. So HC into 0.001 is to HC into 0.002 is to HC into 0.004. We have to take the ratio. Once we take the ratios, ratio means one factor with another factor. It's a division. So HC can be ignored. If HC can be ignored, it can be ignored in the sense, see what is the ratio between these and this? HC into 0.01 whole divided by HC into 0.0002. And what is the ratio between this? So HC into 0.002 whole divided by HC into 0.004. So if you take the ratios, HC cancels. 0.01 is to 0.001 is to 0.002 is to 0.004. This can be also written as 1 is to 2 is to 4 because we are multiplying overall with the 1000. So 1 is to 2 is to 4. So the ratio of the work function is 1 is to 2 is to 4. So this is a right answer to the question and this is a wrong answer. So these two be verified. Okay. Now I would like to see other two options. This is option D. I would like to see the other options. Is it is matching or it is not matching. So such informations I would like to see. Okay. Okay, so the first part I answered, so I am clearing the board. I'll go to the second part. What is the equations for stopping potentials versus 1 by lambda? What is the equations for that? The equations for this is V naught is equal to HC by E lambda minus phi divided by E. This we already learnt. This topic we already learnt. Once we learn this one, we know if this is equal to y is equal to mx minus c format. X means what will be here? Here m will be equal to hc by a and x is equal to 1 by lambda. So now the y is something but v naught and c equal to phi by e. Now tan theta, m is equal to tan theta in mathematics. So this is called slope. So tan theta is proportional to hc by e. Yes, that is correct. It is equal to hc by e and as well as it is proportional to this one. And I want to check the fourth options how this is coming. And the fourth option is talking about, so third options I got it's correct. Which of the following? Statement. So question we have a plural format, right? Statements. I'll put it as statements. We have more than one statements are two here. We are going to see fourth options. Violet color can eject an electrons, eject electrons from metal 2 and 3. So the continuation of this one. So to eject electron, lambda should be less than or equal to lambda 0. Lambda 0. So lambda is the given light. What is the given light will be here? Violet. And the other lights will be, we have lambda 0 1 options, and we have lambda 0 2 options, and we have lambda 0 3 options. 1 by lambda is given. 1 by lambda is given in the graph. Correct. Graph is V0 versus 1 by lambda. So 1 by lambda is given how much? In the graph, we have different metals, right? So this is 1 by lambda and this is V0. So it is 0.001, 0.002, 0.004. So 1 by lambda is 0.01. So what is lambda? So what is the standard wavelength of violet rays? 400 nanometer. 400. This lambda is in nanometer range. So 400 nanometer is less than or equal to 4 options. This 1 by 0.01 means 1000. And another one is 500. This one is 1 by 4. So how much will come? It comes around 250. Okay. So 250. So 4 options will be there. 250 nanometer, 500. So which of the following conditions are true? This condition is true. Okay, this condition is true. Second option, 400 less than or equal to 500 nanometer. This condition is true. And this is for which metal? This is for the first one. So metal 1 it is true, metal 1 it is true, and for metal 2 also it is true, and we'll see for metal 3. So 400 less than or equal to 250. This is wrong for metal 3. Okay, so whenever to eject electron, the wavelength should be less than or equal to the threshold wavelength. Less than or equal to the threshold wavelength. So we'll find the wavelength of these three metals which is given to us. Metal 1, by if you are using metal 1, if you are using violet color, then violet color can eject the electrons from metal 1. Violet color can eject electrons from metal 1. Violet color can eject electrons from metal 2. But electrons cannot be ejected from metal 3 because metal 3 threshold wavelength is this condition. Threshold wavelength is less than 400 nanometers. So this condition is a false. This is a condition to have an ejection. So this condition is a wrong. 400 is not less than or equal to 250 nanometers. That's a wrong statement. So this is not possible. So metal 3, if you are ejecting a white electrons to metal 3, electrons cannot come out. But if you give violet rays to metal 2 and metal 1, then electrons can be ejected out. That's why option D will not be the correct answer. Option A and option C both are the correct answer. Hope you understood the background of this question. Okay, perfectly. Okay, we'll move to the next question. Okay. Okay. This is not a question. I would like to give it as a note. Okay, so that it's very simple. Okay. Next, a note. Note means an additional point. That's a meaning. The below plot. V versus no, let me put it like this one. I versus V. What is called I? What is called V? I is called the intensity. Okay, I is called intensity. What is V? Stopping potential. You can represent it as V0 also. Stopping potential. So a graph which is given will be there. We are going to analyze the graph. That's all we are going to do. Okay, this is graph A, this is graph B, and I have another graph is coming like this one, and this is graph C is also there. This is B, and this is I. Next, look into the representations very clearly. So if you see, you know this value is called the stopping potential. Okay, so I can say, so the following conclusions I am deriving. Okay, so I'll say stopping potential of A and B same, but stopping, okay, but it's not required. So stopping potential of A and B same, because A and B converges to the same point. I will put it as a black color, maybe more specifically for representing B. So B is this one. So stopping potential of A and B the same. Stopping potential will be the same. Next one. Stopping potential different for C with A and B. So A and B will have the same stopping potential. So stopping potential, the stopping potential difference of for C with A and B. So stopping potential is different for C with A and B. So A and B will have same stopping potential. A and B will have the same stopping potential. So let's give it as V01 and let's give it as V02. But one point I am going to say, intensity is higher for what? Intensity of B is equal to C. Intensity of B and C are same, but it is not equal to A. It's not equal to A. Okay, so based on this one, whenever the stopping potential is same, the threshold frequency will be the same. So I am writing the next point. Threshold frequency of A and B same. So what I can written as? I can written as FA equal to FB. This is correct. And here I can written as IB is equal to IC, not equal to IA. IB and IC will have the same intensity, but whenever the frequencies will be the same. See the frequency. So V01, if same stopping potential means same frequency, FA and FB will have the same stopping potential, but this is not equal to FC in additionally. So you should be very careful while this one. So whenever you see stopping potential is same, stopping potential indicate when stopping potentials are same, threshold frequency is same. Whenever the lines, see with respect to I, this is the B and C in the same line, so both will have this much intensity. If you are drawing one line here, you will get this much intensity for B and C, but the intensity, see the intensity will be at this level very high, but for A intensity will be less. So B and C same intensity, and it is not equal to A, it is different. So this is what we have drawn. And stopping potential same for A and B, both are coming to the same line. Stopping potentials are same means frequency, threshold frequency will be the same, but for FC it is different. So FA equal to FB, but it is not equal to FC. That's all. Okay, hope it was clear, the sessions what we have discussed now. Perfectly fine. Okay. So one concept and one problems. So from this, based on the concept, there are a lot of possibility to derive various objective options also. So remember the concept in a very thorough way. Okay. So I hope this concept is very clear to you. So we'll just summarize what is the topic in which we have learned so far. So we have learned about, while we starting the chapters, I told a dual nature of matter and radiation. Dual means two. There are two. Nature means behavior of radiation and matter. Radiation means light will have wave nature and particle natures. Okay, ray optics is talking about lights will have a particle nature. Wave optics is talking about light will have wave natures. Then, so that is a concept. And when we come while through this discussion also, we understood that in through photoelectric effect. So initially light will have particle nature, then science told no, electric the particles will have the light will have wave nature also. Again science told no, light will have wave nature is there. I agree, but at the same time light will also have a particle nature. So who proposed light will have a particle nature? That is called Einstein photoelectric effect. So this is the discussion so far we have seen. Whenever a light of a certain frequency, a minimum frequency of light above which it is hitting on a material, so there is a minimum frequency is required. Okay, so such a frequency or such energy of light is falling on a metal surface and it is higher than the work function of the metal, then the electrons can be ejected out. So because of the light is a particle, it is that particle is coming and hitting one electron and one electron is going out. So this is happening only if light is in the form of a particle. Okay, particle nature. So that is a beautiful science era. Science is initially talking about light is in the form of a particle according to ray optics, Newton's corpuscular theory of lights. Then science comes to Young's double slit experiment, Huygens wave theory of light. These things will be there in wave optics, and it told no, light is not in the form of a ray, light is in the form of a wave. That is another inventions to the science. The later sciences keep on progressing in the era of 1900s. Later after that, it come to the conclusion that no, light will also have particle nature. So it's science is again reverted back. Why? By proving with Einstein photoelectric effects. So this is all about a light have particle nature according to Einstein photoelectric theory. Now we are moving to the second part of the chapter, dual nature of radiation and matter. So dual nature of radiation is over. Next one, dual nature of matter we are going to see. Dual nature of matter. Matter means we have lots of matters in surrounding to us. Whenever I'm taking the classes in front of you, as I told before in my first two sessions also I have told before, I can see camera, I can see light systems, I can see my sound system, I can see mic systems. Many things will be there in the studio systems. So many things in surroundings to me. But at the same time, big object, it's in the form of a particles. So I have camera, it's a kind of particles. I have light system, I have board, I have tester. So everything is in the form of a particle system, particle nature kind of thing. So it's a big one. And we know matter is a particle. So if you are taking a stone is made up of large number of small particles. A stone is made up of small particles, and these particles are called matter. So matter will have particle nature. But our challenge here to prove in dual nature of matter cases, I know matter will always already have a particle nature, but here the context of discussion is that I want to prove that matter also have wave nature. Okay, so I told while we are discussing about ray optics, light will have particle nature. Come to wave optics, light will have wave nature. Then come to dual nature. Dual nature is try to prove light will also have particle nature because of Einstein photoelectric effects. So that is over. So I proved. Now we have a conclusion. Light will have a wave nature and light will have a particle nature. Next we will come to matter. Matter, I already know every matter in the universe is made up of small number of particles. So that is a very well known theory for all of us. But even I am or you also not sure about the cases light will have a wave nature. We are not sure about that. Light will have a wave nature. So that is the things which we are really going to prove it in this context. Okay. So let's go ahead. Fine. Okay. So how should I know a certain character or certain parameter or certain item will have a wave nature? Okay, if something is called I have a wave nature or I have a wave behavior, then some property of the wave has to be above. has to obey. For example, a very basic wave will have different wave nature, different wave related parameters are there. One of the most kind of pronouncing stuff will be wavelength. Pronouncing thing is a wavelength. So wavelength is the property of a wave, right? We can say full wave, we can say half wave, we can say quarter wave, like that we can say. So wavelength is associated with a wave. Important. Wavelength is associated with a wave. A particle will not have any wave. So there is one concept will be there, and that concept is called Debroglie wavelength. Debroglie wavelength. Very important for entrance examination, especially for Neet point of view. I'll expect a chances of coming this question as 99%, but 1% I will always left empty, because there are years without these questions are coming, but majority of the year questions are from their area. Okay, so Debroglie wavelength. What is Debroglie wavelength? We already learned about Debroglie wavelength. We know the equations for lambda. Lambda is equal to h by p. P is called momentum, which is equal to h by mv. This equation is called Debroglie wavelength. This equation is called dB wavelength. I'm writing as a short format. dB wavelength, Debroglie wavelength. Okay, so we have a two context will be here. We have a big particle. If you have a big matter, I'll put it as a big matter. Big matter means m is very high. M is very high. If m is very high means lambda is very small. So I can say lambda is negligible. Lambda is negligible. Negligibly small. And another one is like small matters. What are the very small matters? Whatever we have learned from the science. We know electrons, we know protons. These all etc. are the sum of the small particles. Example, in small particle m is very less. So lambda will be very high, which means lambda is significant. So if a small particle will have a lambda, which means small particle will have a lambda, means lambda is only for a wave nature. So which means small particles will have a wave property. Small particles will have a wave property, and this is the nature of, this is the context, it's called Debroglie wavelength. So Debroglie wavelength is tried to prove, I have an equations for lambda h by p, that is a very well known equation. It's proposed by Debroglie, and h by mb. This is also a variety of, comes from photoelectric effects. This you already know. So when m is very high for a bigger particles, lambda is very small. Lambda is very small means negligibly, it's not comparable. But when you come to m, if m is very small for electrons, protons kind of particles, m is very small, lambda will be very too high, and which is a significant value will be there, which means which is really significant for the context. If lambda is significant value or lambda value is higher, what it is indicated to us? The particle is showing what kind of nature? Wave nature. Okay, the particle is showing the wave nature, or the matter is showing the wave nature. Okay, so Debroglie wavelength is associated with that only. Next, we are going to see some use cases. Okay, we are going to see like different equations. I'll first put it like this one, case 1. Okay. Okay, let me put in lambda in terms of kinetic energy K. Lambda in terms of kinetic energy K. We know an equations for kinetic energy Ke, or K is equal to P square divided by 2m. This is an equation for kinetic energy. So from this one I know P is equal to root of 2mk. Root of 2mk. Okay, or let me put it as kinetic energy itself, then there should not be any confusions. Kinetic energy is equal to P square. So Ke. Okay, so K dot E, let me put it as K dot E. So kinetic energy P is equal to, we'll substitute in this equations for momentum. So I'll get it as lambda is equal to h divided by root of 2m Ke. Ke is called the kinetic energy. This is the equations for Debroglie wavelength if kinetic energy of the matter is given in the question. Then you have to calculate the de Broglie wavelength based on this one. This is one way to write like this one. Another one in terms of potential, because in terms of potential means in electrostatics, simply right, in electrostatic potential, in electrostatics we have W is equal to QV. W is nothing but called kinetic energy or energy. Energy is equal to charged voltage. We can substitute here. So what should I will get? Lambda is equal to H divided by root of 2m into QV, charge into voltage. Okay, so different particles will have a different natures. For electrons will have certain natures, and protons will have certain natures will be there. So we know the standard value of H. H is equal to 6.62 into 10 power minus 35 joule seconds, that is Planck's constant. And for electrons, so mass of electrons will be equal to how much? 9.1 into 10 power of minus 31 kilogram, and charge of electrons will be equal to 1.6 into 10 power of minus 16 coulomb. If you substituted all these values will be here, H, M for electrons. If you substituted, you will get lambda equal to root of 150 divided by the voltage. This is very important. 150 divided by voltage. Here the point is like the voltage, if voltage is given to you in volt, for example 1 volt is given, then you are calculating lambda. This value of lambda you are getting in angstrom. Very important. You are getting the value in angstrom. Okay, suppose you want to 150 divided by root E. This you can also write. What is 12 square? 12 square means 144. 12 square means 144. So root of 150 means what? 12.27 approximately. So this you can written as 12.27 into root V. You can also write this equations like this. So these are same. So this equation is again same. Very important. 99% chance to ask this topic, de Broglie wavelength. If voltage is given root of 150 by V, you will get angstrom, and root 150 means 12.27 divided by root V. This is also V should be in voltage and lambda should be in angstrom. So this area is quite important to know. Okay, so this is a very short descriptions, and let's make this as case 2. So case 1 will be there and case 2 will be there. So both has to be learnt in terms of angstrom or in terms of voltage or in terms of kinetic energy. Okay, so I'll stop it here. Again, a couple of sessions are required to complete this one, and we have a few questions will be there to discuss it. Then we'll move to the the final topic of the section, which is called a Davison's-Germer experiment, that we'll learn it in the next class, so that this chapter will be over. So the next sessions will be the last sessions of the theoretical sessions from this chapter. Okay, so thanks for watching the video once again.